40%. Negative effect because we didn't. Possibly we should have a negative effect, but we didn't do like a mixed ion. We just try with the binary. One is the potassium, calcium, magnesium. So I don't see that it happened for the different ion impact. But yeah, it could be possible when you mixed all the ions together. Yeah, thanks.
Last question, okay. So.
Thanks for your nice talk. I'm Qinghai Wang from Yangtze University, and I read a lot of your paper when we're working on the selectivity. So it is able to conclude that as long as we are able to decorate the membrane or anything with specifically size of layer, a layer with specific size, then we are able to selectively remove or extract for the example, the lithium, potassium in a sequence. Thank you.
So his question is about in terms of size, we have a selectivity, how we can improve, right?
Yes.
So, okay. So ions, it's very complicated. It's not like your atomic ion represent your hydrate ion, dehydrate ion, also combined with your different ions together. So that in fact, what you're saying is the lithium is, let's say 0.16 nanometer, very small size as an atomic level. But when you have a hydrate, so water molecule is the surrounding in your atoms. Yeah. So they have a different size, they're like a bigger. So that when you have this kind of the hydrate, dehydrate, also you have a different counter ion as well as the same ions. That you have also a different way of the size can be decided for your selectivity. That's the reason why when you have a GIF material, even though you have around 3.5 angstrom, your size, but your atom of the lithium is around 0.16 nanometer, 1.6. It's much smaller, but in general condition, they cannot pass through because they are hydrated. And then you have to remove your water molecule surrounding your lithium ion, and then you will push it through your GIF channel. That's the reason why half size will be the passing through your channel, and then you can be easily store in your lithium, in your electrodes. So your question is very difficult to say only size, but also hydrate and then different water chemistry involved when you have a more selectivity. That's the reason why this is a lot of the research you can continue.
Thank you. So because of the time limit, I believe you may have some more questions for Professor Xiong. Please capture him during the coffee break. Okay, please join me to thank Professor Xiong again for his wonderful presentation.
Thank you. Thank you.
Okay, it's time we move on to our next keynote speech. Our next speaker is Professor Qilin Li from Rice University, Rice University, United States. Okay, I think she's a professor in the Department of Civil and Environmental Engineering. Okay, I think Professor Li, actually, her major field is for the water reuse and wastewater treatment. I think she combines with the nanomaterials and a lot of separation technology. I think she works on nanomaterials for volume control for the membrane. Also, last year, I had the opportunity to listen to his speech about using, combined with the nanomaterial with membrane distillation. I think she did a very great job in combining these two technologies together, reaction and separation. Because of her wonderful research, I think she received a lot of awards from the Rice University and from United States. But I just mentioned A major one is she's now a fellow of the IWA Society. Okay, and also you know her as the editor of the Desalination Journal. Okay, so please join me to welcome Professor Li, please.
Thank you for the kind introduction. Good morning, everyone. My original title is Achieving Ion Selectivity in Electrosorption and Electrodialysis. And when I get to finish electrosorption, I realize I'm already on slide number 36. So I apologize, I removed my work on electrodialysis. I'll focus on how to achieve ion selectivity in electrosorption in the talk today. Many of you probably haven't heard. I'm having the same problem that everybody else had. Not proceeding. Oh, this one. Okay, the wrong direction. Got it. So now many of you have heard about Rice University. We are located in Houston, Texas, right? You probably, only thing most people know about Houston, Texas is we are the cowboy country. We're actually a lot more than the cowboy country. We're the #4 largest city in the United States. And is the energy capital of the world. Most of the energy companies have their North America headquarters in Houston. So oil and gas and renewable energy are one of the biggest support industry in the city. And we're also home to the NASA Johnson Space Center, which controls all the flights of NASA. We have the world's largest medical center, which is right next door to our campus, Texas Medical Center. So this is a picture of our campus. Right next to, so you can kind of see the, oh, actually you can't, it's on this corner of the Texas Medical Center. My office is right there. You can see kind of my window. We are a fairly small private university in the US, well-ranked, but very small. We have just a little bit over 4,000 undergraduate students and 3,000 graduate students. So it's a research intensive university, so a very strong engineering program. Now, I'm also here representing our NASA funded engineering research center called Nanotechnology Enabled Water Treatment, NEWT. This is the first national center that develops water treatment technologies based on nanotechnology. And it's a partnership among Rice University, Yale University, Arizona State University, and University of Texas at El Paso, together with more than 20 industry members. And the goal is to form an innovation ecosystem to develop novel decentralized water treatment systems using novel nanomaterials, nanotechnology, and processes. The center has a large number of faculty members involved, and we support also a very large number of graduate students and postdocs and undergraduate students. What we are trying to do is really change the paradigm of water treatment from this very large centralized water treatment, conventional water treatment plants to decentralized systems using the unique advantages of nanotechnology, which is that it allows us to miniaturize materials, to miniaturize processes and intensify processes. And another transformation we wanted to promote is a transformation from conventional tank reactor, chemical reaction-based treatment processes to more modular, catalytic, and physical process-based treatment systems that are that produces less sludge and also more compact and easier to deploy. So my work has, as our chair mentioned, primarily focused on developing nanocomposite membranes or thin films and use them in different water treatment processes. So we've worked on utilizing photothermal nanoparticles, so nanophotonics, nanosorbents, as well as two-dimensional nanomaterials and different photocatalysts and electrocatalysts in a polymeric substrate, and so that we can utilize the properties of the polymer, which allows us to enjoy some of the nice bulk properties, such as electrical conductivity, such as elasticity, as well as the unique functions of these nanomaterials, right? So having this substrate also allows you to strategically co-locate nanomaterials of different functions so you can achieve synergy between different processes. So today I'm going to focus on this one aspect of nanocomposites, which is when you embed selective nanosolvents in a polymeric substrate for ionic contaminant absorption or transport to achieve ion selectivity in CDI or electrosorption processes. I'm a water treatment person, so we are not foreign to the idea of separation or selectivity, right? In water treatment, we use a myriad of membrane treatment processes are trying to achieve selectivity between water contaminants and water molecules, right? That most of the time is relatively straightforward because the water contaminants and water molecules usually have very large differences in terms of size. So a lot of our previously focused on processes are based on separation in size. Now, in membrane field, one of the biggest challenge in this separation efficiency is the paradox or the trade-off between permeability and selectivity, right? So here is some data we collected for a review article we did a couple of years ago where we looked at water permeability versus water salt perm selectivity. So this, you can see this as separation between water and salt, and this is membrane permeability. We looked at both commercial membranes as well as novel membrane materials that you can find in the literature. And you can see that most materials are bound by this selectivity permeability upper bound. However, in recent years, a few novel materials emerge that has way above that upper bound for this selectivity permeability trade-off. And few, but they are all, with no exception, some sort of nanomaterial based on graphene or carbon nanotubes. You can also see here, this is another set of data where this is, that's mostly for reverse osmosis membranes. This is for mostly nanofiltration membranes. Here we actually see, we're looking at monovalent, divalent selectivity versus water permeability, right? Here you see a number of new developments that showed improved selectivity permeability relationship, and they kind of push the boundary up this way. Some of them are actually based on improvement a traditional synthesis method. So there are ways to break through the performance upper limit here. Now, Professor Xiang mentioned the challenges in separating ions. Ions are a bit tricky. So if you want a very precise separation between the different ions, right? So there are ions that have similar charges and also very similar hydrated ion radius, especially in the cation. So that you can see here in lithium recovery, one of the biggest challenges is actually separating lithium from sodium and potassium, and they have the same charge and very, very similar. Oh, how did I go back? And very, very similar hydrated ion radius as well. And another challenge is also to separate the monovalent from divalent, just because of the scale formation issues, and also in lithium separation, the precipitation of this divalent cation is one of the reasons that leads to very high loss of lithium. I won't have time to talk about the lithium sodium and lithium carbonate calcium separation today, but we've been actively working in this space. On the anion side, you can also see that chloride being the most abundant anion in a lot of the brines and our natural water streams. It actually has fairly similar hydrated ion size as nitrate, right? So nitrate is one of the target contaminants we do want to remove from groundwater. And you have other anions in water that have fairly similar structures, sulfate and phosphate as well. And a lot of times separation among these becomes a challenge. So I'm going to give you a few examples of the two different approaches we have taken to achieve ion selectivity in the electrosorption process. The first approach that I will talk about is a selective nanocomposite coating on electrode surfaces. Professor Shang briefly mentioned about this in his talk as well. So the approach is fairly straightforward. We put a thin coating, nanocomposite coating on the electrode surface. In this coating, so you have a polymer substrate and you put these nano-sized sorbent materials that have high selectivity for your target ion, right? So the concept is very straightforward. We're hoping that the target ion, the ions will be transporting the thin film, right? And we're hoping the target ion will primarily transport through these nanosorbents because the nanosorbents are selective or selective towards the target, and you will have higher flux for your target ion compared to the competing ion. But you will notice that if your substrate is not chosen properly, because they are also going to transport through the substrate as well. And this is something that I don't have time to talk about today, but we are actively with some very good solutions to this. And this is why sometimes you will use a sorbent that has very high selectivity, but once you put into this nanocomposite coating, you see a small improvement in selectivity, right? And this is because your transport through the substrate is actually faster than the transport through these nanosorbents. And we do have a solution to that. So the first example I give you is some older work where we try to develop a selective CDI process for scaling ion removal. So calcium and sulfate are of interest in this study for us. So the idea is very simple. We put in chemical functional groups that are selective for calcium and sulfate. And we use also a substrate that can serve at the same time as either a cation exchange membrane or anion exchange membrane. So you have a thin coating that serves both as your ion exchange membranes in the MCDI process, at the same time have high selectivity for your target ions. The way we did that was we actually took commercial chelating resins. So this is a commercial calcium chelating resin, and we mill it or grind it under cryogenic conditions so that they become nanoparticles. And it's very important for them to be in very small size. And I'll explain a little bit later why it's important for them to be small. And we mix it with our cross-linker and our monomer, which is in this case sulfonated. So we have a cation exchange membrane. And we float coat it onto the carbon electrode surface. And you can see here the coating, you can find features of the original calcium chelating resin in that coating. So clearly you see if we measure ion transport across this thin coating. So this is the flux of calcium and sodium across the thin coating. And you can see calcium transports across the thin coating much faster than sodium. So this confirms our hypothesis. If you have faster transport, faster flux through this, and then your electrodes actually sees higher concentration of your target ion, so you get more absorption on the electrode. So we're not changing the absorption capacity, but we are making the electrodes seeing different concentrations of the ion. And so here are just some results to show you that selectivity. So this is the uncoated active carbon. You can see here, sodium actually absorbs faster than calcium, but once it's coated by our selective coating, you can see calcium absorbs similarly in terms of kinetics as sodium, but has much higher absorption capacity compared to sodium. Is because now the electrode actually sees higher concentration of sodium, and this is calcium. And this is also saying here, you can see on the electrode, this is how much is absorbed on the electrode at different sodium to calcium concentration. You can see that after you have the coating, even though we still have the same carbon, and the coating doesn't add to any absorption capacity, by the way, but you have a much bigger portion of the carbon that's being occupied by calcium instead of sodium. And so this leads to a selectivity factor of up to 5.4. So still a significant, well, not a very high selectivity because the original resin has a selectivity of more than 100. And this is exactly because our substrate is actually not selective, right? Again, this is something we're working on right now, and hopefully next year I will be able to share with you more. And similarly with sulfate, this is the case where I'm going to show you the impact of particle size. So with the sulfate resin, we were not able to grind it to as small as a calcium resin. So these are actually a couple of 100 nanometers in diameter, sometimes even bigger, up to 500 nanometers in size. We saw very similar phenomena. We saw faster transport of sulfate compared to chloride in this simple transport experiment. Here you can see clearly we have higher selectivity with the resin, the nano-sized resin added compared to if you just have the polymer coating. But we also see a very interesting drop in the charge efficiency when you have the particles added. And this is why I wanted to, why I said earlier, the size of the particle is actually very important. The smaller the particle size is, the more perfect the particle and polymer substrate interface is. So when you have very big particle size and you embed it into a polymeric thin film, and you often have large defects around the particle, so your cations will go, this is an anion exchange, cations will go straight through, so you lose charge efficiency. The coatings can actually last pretty long and also serve the good protection for the electrode because we have the ion exchange function as well. So you can see here, we are able to run a very large number of cycles and still see very reproducible performance over time. The selectivity doesn't drop significantly. Well, it does drop to some degree, but not too much when you increase the chloride to sulfate concentration ratio, similar to what we have seen with calcium as well. So these are basically some older work showing you that if you include selective nanosolvent in the electrode coating, you do get improvement in selectivity, but you don't get a huge improvement. And the key is really working on that ion exchange polymer substrate. Okay, a second approach I wanted to talk to you about is to introduce absorption, selective absorption site on the electrode itself. So yesterday, Professor Xiao Shu talked about his work and how you can kind of trap PFAS on the electrode. And so this is fairly similar approach. And here our target is nitrate and chromate. And so both are notorious groundwater contaminant. So this work was done by, in collaboration with Professor Xiaoyan Li and his student Jiao Chen at Hong Kong University. So here we took an interesting approach trying to utilize bio-waste. And so we took eggshells and get rid of the inorganic part and save the organic part. And we carbonized that eggshell membrane. And we directly utilize this eggshell membrane as an electrode. And of course, there's a reason why, and you will see later. And we use this electrode in the CDI process and look at nitrate removal. So here are some SEM images of the eggshell, carbonized eggshell membranes. And you can see it's a highly porous network, but it has fairly low specific surface area because this material is not activated unlike your activated carbon. So it doesn't have any micropores. It has very large pore sizes. So here you can see fairly distinct 3 pore size regions. And as a result, has very low specific surface area compared to this is a commercial activated carbon. However, this material has significantly higher selectivity towards nitrate compared to activated carbon. So here are some results for our single-solute electrosorption experiment. I didn't show you the activated carbon, but the activated carbon basically showed the highest absorption for chloride. And here you can see nitrate among all the anions we tested has the highest absorption. And you can also see here that it also has the highest charge efficiency for nitrate. It has much higher capacitance when nitrate is an anion instead of chloride. And when you run experiment in a mixed solution mixed salt solution, you can clearly see here has almost no absorption or very little absorption for the other anions, but much higher absorption for nitrate, right? This is compared here. We not only have a much higher overall anion removal, most of the anion removed is nitrate, and very distinctly very high removal for nitrate. Right? And if you look at the selectivity relative to each competing anion. So here is a nitrate versus chloride, nitrate versus sulfate, and nitrate versus phosphate. Without exception, the carbonized axial membrane has much higher selectivity for nitrate compared to these others. So the highest selectivity we were able to reach was 10 with respect to sulfate and phosphate. Let me see. And we also compared the selectivity we achieved in the study with other electrode materials that have been reported in the literature. And so we claim, at least based on what we found, that this material has a higher selectivity for nitrate. However, the biggest problem is because of the very low specific surface area, the absolute amount of nitrate ions absorbed is still very low. So our next step of work is to activate this material so we can create micropores in it so that you can not only have high selectivity, but also high absorption capacity. Now, I said I will tell you why these axial membranes have high selectivity for nitrate, and there was some earlier work that doped carbon with nitrogen and showed selectivity for nitrate, right? So this is protein, so naturally has nitrogen residual. Even when you carbonize it, you still see significant residual of nitrogen. So there's about over 13% nitrogen in that carbonized axial membrane, and it has a variety of carbonaceous functional groups we could find. And our DFT calculations show that these carbonaceous functional groups has very high affinity for nitrate compared to chloride or sulfate. So these are the bonding energy from DFT calculations showing how these nitrogenous sites binds to nitrate more strongly than chloride or sulfate. And so that was primarily responsible for the high selectivity we saw in our electrosorption experiment. Another study we did was for hexavalent chromium removal. So hexavalent is a notorious groundwater contaminant. Many of you might have seen the movie. Aaron Brockovich was one of my favorite movies when I was a graduate student in the environmental engineering program. So hexavalent chromium is highly toxic. It's a known carcinogen. So group 1 carcinogen, meaning it's known to cause cancer in humans. And currently, the US EPA regulates it at a fairly high level. So 100 ppb for total chromium, because chromium 3 can transfer, or chromium 3 and chromium 6 are actually converted to each other fairly easily. But chromium 3 is actually a necessary element for our health. And so it's an essential human dietary element. Some more recent studies find that the chromium 6 toxicity level is much higher than what we had originally thought. So California back in 2014 had set the standard at 10 ppb, and recently was talking about 0.02 ppb. So that was their proposed level. And if you look at that, and the drinking water in the United States, a large area of the US, if we set the regulation to 10 ppb, not to mention 0.02 ppb, will be violating the drinking water safety level. So hexavalent chromium could potentially be a very large problem in drinking water, at least for the United States. So for this contaminant, what we did was we actually used a highly selective moth. And this is a moth that not many people have heard about. It's a moth with a cobalt metal center. So with a 1245 benzene tetracarbonate, found a organic part, and also I think was a 4,4 bipyridine. It's a pillared, layered moth material, but it happened to be, well, so it has very high hydrophilicity, unlike most other moths where that you need to do post-treatment to make it hydrophilic and therefore compatible with your polymer substrate. This is just inherently very hydrophilic and also happens to have very high selectivity for both arsenic and chromium 6. So chromium 6 is usually present in water in the form of chromates, so ArO4 2- or Cr2 or dichromate, so Cr2O7 2-. And so, however, moth materials are not conducting, right? So it's difficult to use moth directly in an electrode. So what we did was we synthesized this moth in the presence of graphene oxide. So we just add graphene oxide flakes into the solution in the sulfur thermal process. And what happened is we were able to form the moth on the surface of the graphene oxide. At the same time, the reductive condition of the synthesis reduces the graphene oxide to graphene. So you end up with these flakes of graphene with a very thin layer of this cobalt moth on the surface. And so here you can see a very uniform distribution of the cobalt and nitrogen, indicating nice coverage of this moth on each individual reduced graphene oxide surface. And what benefit does this have? This now makes the material electrically conducting and can be used now as a good electrode material. So you can see here the change in the electrical conductivity. So the original GO or moth are not conductive, but once you form the moth on the reduced GO surface, we have very high electrical conductivity. It also improves the absorption capacity for hexavalent chromium. So here you can see this was the original absorption isotherm for the cobalt moth itself. And once you add the reduced GO, the absorption capacity dropped because GO doesn't have much absorption capacity for chromates. But if you add an electrical field, now you see significantly enhanced absorption capacity compared to this material right here, right? And this is because the electrical field leads to higher local concentration of the hexavalent chromium and therefore higher absorption capacity. You can see here the saturation capacity didn't change. That means we didn't really add additional absorption sites. Okay, so some performance data here. Because we have both electrosorption and physisorption happening at the same time, these moth materials are very good physisorption materials for hexavalent chromium. So you can see our absorption capacity is actually a strong function of a desorption voltage. If you have 0 volt versus negative 1.2, negative 2.5, and 4.0, you can see increasing absorption capacity of the electrode material, right? So this is a strong indication that some of the physisorbed chromate is not being released when your desorption voltage is too low, so it requires much higher desorption voltage for you to make these absorption, to regenerate these absorption sites again. So I wanted to make another point here to highlight the selectivity compared to the chloride. So again, this is the data obtained at a desorption voltage of negative 2.5 volts. So here you can see the absorption for hexavalent chromium is much higher than that for the chloride. And that's summarized here in this graph here. We're showing ion absorption in mole or millimole per gram of the electrode as a function of desorption voltage. And you can see here, the absorption for hexavalent chromium is significantly higher than chloride under all conditions. And the selectivity is much higher than the control materials, activated carbon or the reduced GO without the moth. For these two materials, you actually have much higher chloride absorption than chromate because here you have primary electrosorption, but here you actually have selective physisorption on the moth material itself, right? So you have a fairly high selectivity compared to these control materials. And you also see a slight increase in selectivity when you increase the desorption voltage, as I explained earlier, because where the higher desorption voltage is regenerating the sites better than low desorption voltage. Now, If you just use the electrosorption or the CDI process, you still generate a brine stream that has hexavalent chromium, which is toxic, right? So one of the advantages of this process is actually quite similar to what Xiao showed yesterday. You have this chromium-6 fixed on the moth pore side, absorption sides. And when you reverse the voltage, the chromium-6 is actually reduced to chromium-3, which is non-toxic now. So you can see here, during the desorption process, there's a significant portion of the chromium-6 being reduced to chromium-3, and that portion increases when you increase the desorption voltage, right? So here you have what we call the trap and degradation process. You trap the chromium-6 on the selective side, and then you reduce it to chromium-3. And the impact of desorption voltage is also showing here with increasing charge efficiency when you go to higher desorption voltage. So we are actually exceeding 100% charge efficiency. Okay, so this is a weird way to show that you have more than 100% charge efficiency. And again, this is because you have physisorption that's not caused by the electrical charge on the electrode. And when you use a high desorption voltage, you regenerate this absorption side, so you end up with higher than 100% charge efficiency. And you can also see here the difference between the charge efficiency calculated during the absorption cycle versus the desorption cycle, because we have the reduction of the chromium-6 to chromium-3 in the desorption cycle, and that's consuming some of the electrons, right? So it's very clear here. And this was also confirmed when we analyzed the electrode. So we took the electrode out after the absorption cycle. So here you can see after the absorption cycle, you have most of the chromium on the electrode being chromium-6, and you have a small amount of chromium-3 from the previous desorption cycle, and you're almost no chromium-0. But if you take the electrode out after the desorption cycle, and you can clearly see here, we have almost no chromium-6, very little. And you have primarily chromium-3 and chromium-0. So you have significant reduction of the chromium-6. So most of the chromium-6 are released and the rest of them are reduced, and there's a small amount of residual chromium-3 and chromium-0 on the electrode surface. This was also able to be explained by the various reactions happening on the electrode surface. So with that, I wanted to conclude my talk in trying to show two main points here. Nanocomposite coatings can provide selectivity if you have these highly selective nanosorbent particles in them. But as I said earlier, we're still working on this, right? The substrate itself is also very important. And the same idea can be used in ion exchange membranes for electrolysis, because we're really controlling the transport, not absorption. And if you include selective site and that has strong specific interaction with your target ions, you could also create selective sorption in the CDI process, which could, in some cases, for redox active contaminants, create benefits of electrochemical degradation. With that, I'd like to thank the many collaborators that I worked with in these few studies, and thank you for your attention.
So let's thank you, Professor Lee's next talk. So now I think we have time for Q&A. Michelle.
Yeah, thanks, Qilin, for the great talk. I'm actually sort of very intrigued when you put these nanocomposite onto the membranes. It looks a lot like when they use these mixed matrix membranes for gas separations. And whenever they do the gas separation, my question has always sort of been why, and I know you're working on it, but why don't, in this case, you create a very thin layer of the nanocomposite that's continuous and self-standing instead of making it like a mixed matrix?
Yeah, so it's hard. So we try to increase the percentage of the nanosorbents, right? And to some extent, the film becomes very brittle. So that's why the polymeric substrate is actually very important. So you can get it to a certain point, which would give you a much higher selectivity and also higher flux, but you still need the polymer bond because it's kind of serving as a binder. So there is a limit.
And if I can, like a very quick follow-up, is there a known sort of percentage of the sort of inorganic component in the matrix that allows for, I don't know, like total percolation, but no side flux?
Yeah, so the percolation threshold is a known parameter for people to use. So most people think if you reach the percolation threshold, at least you will have continuous flux of the ions through the polymer. But of course, your selectivity still will be lower than the original nanosolvent, because as long as ions can pass through the non-selective polymer matrix, you will still suffer, right? Especially the transport through the polymer, a lot of times is actually faster. There's less resistance. So, some people took the extreme approach, right? So for a cation exchange coating, they put anion exchange polymer there. So you can get really high selectivity, but then your ion flux gets really low. And so your ion flux there, it completely depends on the percentage of the nanosolvent you can put in, right? So yeah, so there is definitely things you can play with, but there is an upper limit.
Thank you.
Thank you for this nice overview. I think CDI is already part of my life quite a bit, but now it will also be each time when I enjoy eating an egg. I have a question on that part. So you nicely showed XPS data and also DFT went a little bit into the mechanism. I was also wondering myself, how about the hydrophobicity? Because the 4 ions you studied in this particular work, the nitrate one, although the difference with chloride is very small, but it's the most, let's say, less hydrated one. That can be most easily dehydrated. Could it be that also this has a role in the mechanism?
For the nitrate, in this case, we don't have a polymer substrate, so the moth is directly grown onto the geo surface, so the ions have direct access to the site. There's not a transport part through any coating.
But it was the protein, right? So it was the nitrogen protein container.
Oh, sorry.
So
I'm
this is the other
talking about
project.
the nitrate one.
Yeah.
The nitrate one on the axial. That one is also a direct absorption on the outer surface. This one, the carbonized axial membrane doesn't even have any internal pores because we didn't activate it, right? That's why the surface area is so small. So that it's not transport limited. It's really surface reaction limited. So it's the binding strength.
The supposed interaction is due to the high amount of nitrogen atoms. There is a preference for nitrate. That's then
that's our conclusion.
Yeah.
Or not conclusion, hypothesis.
Yeah.
Right? Was based on DFT, we don't have any direct experimental data to confirm.
Yeah. Thank you. Thank you.
Right.
Yeah, and thank you. So we still have online questions.
Okay.
So the first one is
larger electrodes are possible to fabric large.
Okay. Two questions here.
Very good question. So these are all very small that we made, but the biggest one we made are maybe about 30 centimeter in diameter. So we have cylindrical reactors. So our electrodes are actually circular. So the biggest one we made are about 30 centimeter in diameter, but nothing bigger than that.
So the question from the audience here. Yes.
Thank you for a great talk. Regarding your nitrate chloride work, I'm just wondering if you have investigated the effect of applied voltage or potential on the selectivity. So
for that one we did not, because when you use negative 1.2, you already completely dissolve everything.
When you you just applied 1.2 volt, and then I wonder if you applied 0.8 or 0.6 or something.
Or lower ones. No, we did not.
Okay.
That one we did not.
And one more question is that when you release chromium and at negative 4 volt, do you see any possible degradation of your material because that's too harsh?
So we have our working electrode, and the counter electrode is the active carbon electrode. Our working electrode was never exposed to high oxidizing condition because the absorption is always done at 1.2. It's a desorption, but it's a negative voltage, so it should be okay. It's more, I'm more worried about the counter electrode, the active carbon electrode, but we run these over 100 cycles. Our cycles are actually pretty long because we wanted to wait until absorption reaches equilibrium. So our cycles are 30 minutes. So we run over 100 cycles and we took SM images, we monitor pH swing, and surprisingly, we didn't see it because I was expecting some degradation of the active carbon electrode, but surprisingly, we didn't see any. But that's a very good point. Over long term, I think there will be issue on that active carbon electrode.
Okay, thank you. So one more question for Alicia. So yeah, the dissolution voltage of minus.
Oh yeah,
2.5,
so
yes.
that's what I think I was
Okay.
trying to explain. I think there's definitely water splitting happening on the carbon active carbon electrode, but we did not observe any detectable damage on the active carbon electrode, and neither did we see any degradation of the performance, luckily. But we only tested up to maybe 120 cycles.
Okay, so thank you, Professor Lee. Let's talk again.